Okay, how do X-rays work? Long story short is X-rays are electromagnetic waves, and their energy level is higher than the visible wave spectrum, but is lower than the gamma wave spectrum. We care about X-rays because we can use them in medical technology to image all sorts of matter that is relevant to the human anatomy in different types of densities. And of course, it has its limitations. So the principle of X-rays is based on a cathode ray tube. And a cathode ray tube is a glass tube that looks something like this. Okay. And it's got a cathode emitter on one side. Let's say it's this whole thing, for example. Cathode's negatively charged. And at the very opposite end, it's got an anode, which is positively charged. And in the middle of the anode target is going to be this little piece of metal, usually made of tungsten, which is what the electrons, which are being emitted from the cathode, are essentially going to hit. Now, this anode is actually connected to basically a motor system, which is going to cause this whole target to rotate in circles. And why does it do that? Because only 1% of the electrons that actually hit this target get converted into photons, which are X-rays. That means 99% of the energy that's hitting this target is getting dissipated, and we know that dissipated energy is heat. The problem is that this whole thing is essentially a vacuum system, and so it cannot handle that much heat being generated. So in order to kind of avoid that much heat from being generated all at once, this motor rotates the anode the whole time in which these electrons are hitting it, so that not one spot gets overheated. Now, I guess if I were to, if this were physics class and I were to complete the circuit would look something like that. Now, the whole point of this video is to try and explain to you that this is a two-part process. And the second part of the process is that these photons that are generated are going to hit matter, which is essentially the human body. And after it hits matter, hang on one second. After it hits matter, it's going to hit a photographic plate, right? Photographic plate. And this is going to produce the image that we finally look at, the X-ray image. Now, before I get into the specifics of each one of these steps, I just want to mention just kind of the way in which X-rays were discovered serendipitously. And in 1895, there was this German physicist, his name was Wilhelm Röntgen. Okay, and he was playing around with basically this model of the cathode ray tube. Okay, so he had this, the cathode, the anode, the electrons were hitting it, and this was, made of glass, and then he had this covered in like cardboard or something, the story goes. And so he had this whole system set up, and just kind of by chance, he happened to have this kind of screen set up nearby where he was conducting his experiment, and he noticed that the screen kind of ended up having an image produced upon it. And so Röntgen was like, what's going on? How is it possible that there's an image that's being created here? And so he kind of realized there must be these unknown waves of radiation that are being emitted from this cathode ray tube. And I don't know what they're called. They're unknown. In math, we call unknowns X. So we'll call these X-rays that are producing this image over here. Roentgen. Worth knowing that name because a lot of board questions might have like Roentgen image is one of the answer choices, and unless you knew that that was like a prehistoric way to name X-ray images, then you might have gotten the question wrong. I know that happened to me one time, but luckily I was prepared beforehand. Anyway, so this was 1895, and he discovered electromagnetic waves, right? So this is the setup that he had. Now, let's kind of break down this process a little bit more. Once the electrons hit the anode, there's two interactions that are happening in this moment. Why is this important? Because the interactions that are happening at this junction results in a loss of electron kinetic energy, which is essentially how these photons are being generated. So there are two ways in which these electrons are losing kinetic energy. Number one, the electrons are finding their way towards the nucleus of these tungsten atoms. And once they come towards the nucleus of the tungsten atom, they kind of bend away in different directions. Okay? This bending process contributes to the loss of energy. This is called breaking radiation. And number two, electrons lose kinetic energy from electron-electron interactions. This should remind you of general chemistry, in which the electron kind of approaches these different shells that contain electrons within the atom of the tungsten. And as the electron approaches, some electrons from the outer shell bounce in towards the inner shells, and this movement of electrons from the outside to the inside also contributes to this loss of energy. Okay, so we get that electrons lose energy and thereby get converted into these photons, meaning X-rays. So let's think of this whole process happening, as I said, in two steps. Number one, loss of electron kinetic energy. And then number two, what's happening down here is kind of absorption of electrons. Now, the image that is produced is going to contain different types of densities. Now we know that the denser matter on X-rays tend to be bone and metal, right? And here's an interesting point to make about them. Bone and metal tend to be composed of atoms with higher atomic numbers, okay? For example, bone has calcium, which has an atomic number of 20. Metal, for example, like platinum, I can't remember its exact number, but it's a very high atomic number. And if it has a very high atomic number, it means it's composed of many, many, many atoms. That means that when these photons hit bone or hit metal, which in and of itself is composed of lots of atoms, a lot of energy is going to be absorbed. So this is going to be a very high amount of absorption. Okay, and that means that These are going to be more dense, right? These are going to be radio opaque, right? But at the same time, not all of the energy that hits a matter is going to be absorbed. In fact, the alternative is that the energy gets scattered. It does not get absorbed. And we know that the matter that has the least amount of absorption, which just kind of pass right on through, most significantly is going to be air. But again, the ones that have less absorption than bone and metal, only muscle and fat. And if you think about what I said before about atomic numbers, air, muscle, and fat tends to be composed of atoms that have smaller atomic numbers. For example, carbon, which is 5, hydrogen, which is 1, oxygen, which I believe is 8. They all tend to be less, which again means that there's less for these photons to kind of bump into and run into. And if they're not bumping into or running into anything for which it can get absorbed, it is just going to pass right on through, okay? So we can basically say that this has a lesser amount of absorption. This is less dense. This tends to be more radiolucent. Okay. Thereby, we end up with a plain film X-ray in which the white part of the image tends to be brightest metal, then bone, and in gray we end up with muscle and fat, and air will tend to be black. The most important thing about understanding how X-rays work is number one, that there's 2 steps to it: the loss of kinetic energy, which is happening in this first step, and then the absorption of these X-rays, which is going to happen between the human body and the photographic plate. Now, there are so many limitations to X-rays, mainly being that you're only seeing pretty much one 2-dimensional picture at a given point in time. We can't really see things in 3D, which means that of all of these X-ray particles that are hitting the human body, we can't really focus in on the tumor or the lesion that we want to see. We end up with a lot of junk information that's not really relevant. We get around that by, instead of taking a 2-dimensional image, we take multiple 2-dimensional images, and we kind of compile them all together to form a 3-dimensional image in which we can have a CT scan that will tell us the size and the depth of the pathology that we're looking at, and that in most cases will be more relevant to us. But I hope this helped understand how X-rays work, just, the very basics. Because knowing this will help you understand intuitively how CT scans are different, and thereby how MRIs are different. Okay, thank you.